Chris, who apparently doesn't get out much, but is right here, so he does get out occasionally. And he's going to be talking to us about Kalman filters, which I know absolutely nothing about. So with that, please join me in welcoming Dominic.
Thank you. So this seemed a cracking idea when I first proposed the talk. So I've implemented Kalman filters several times and authored a library, which I'll talk about a bit later on. And I thought I'd talk about how types help me get it correct. And then as the time to do the presentation got nearer, I realized I've got to explain how Kalman filtering works to do something about the implementation. And that, I think when Chris was talking upstairs, I don't know who was there, talking about how they have 8 lectures to get to something about geometric algebra, I thought, well, yeah, the Kalman filters, there's a lot of algebra, there's a lot of equations, and I don't really want to do that because Simon Thompson told me every time you have an equation on a slide, you lose half your audience. So if you, the geometric, by the end of it, you'll have one person that might understand. Anyway, so what I've tried to do, and you'll be able to judge how well I succeeded, is do an intuitive view, I hope, of why Kalman filtering works. Then I'm going to spring some equations on you, because you need the equations to do the implementation. And then I'll show you how types helped me do that implementation. Right. So the hard bit is the first bit, for me anyway. I hope not for you. Okay, so this is 1968. So Kalman filtering has been around since the 60s. It was used in the Apollo 8 mission, apparently. The one that went behind the moon didn't actually land on the moon, I think. So the W matrix is one of the matrices, presumably, in the Kalman filter. So I'm going to play a game with you. Now I'm going to select a number at random from a normal distribution, and I'm not going to tell you what that is. And I'm going to give you some data. At time 1, I'm going to tell you, I'm going to take my number I've sampled, I'm keeping secret, and I'm going to give you a noisy version of that secret number. And I want you to guess what my number is. You'll never get it completely right, because I'm not going to give you enough information for that. But you ought to be able to do better and better each time I give you some more information. And so obviously, the first thing you reach for is Bayes' theorem. So Bayes' theorem is almost trivial, right? So the definition of the probability of A given B is the probability of A and B divided by B, the probability of B. The probability of B given A is the probability of A and B divided by the probability of A. So therefore, the probability of A given B is proportional to the probability of B given A times the probability of A. That is Bayes' theorem, right? So it's almost trivial, almost content-free, you say. So I'm giving, do you remember I give you some information. I'm going to pick my number from a normal distribution. So I'm not going to, and how I'm going to do this, I'm hoping to make this a bit sort of intuitive, is I'm going to create a histogram of that distribution by sampling from a normal distribution. So that's what the normal function does. Run a sampler, create a histogram. So there is my histogram. So that's what you know. Or alternative, they're all your guesses, right? So you've guessed lots and lots of times what my number might be. So I've sampled my number from that distribution. Happens to be 1, why not? Highly unlikely. Well, every value is highly unlikely, isn't it? Any value will have a probability of 0. Now I'm going to tell you the model. So this is where I say I'm giving you noisy versions of my number, right? So my number is theta, and I give you a bit of data, and I tell you how close the data is to the value I selected. And it happens to be the probability density function for the normal distribution, but it could be anything, but we want it to be that, because that's what the Kalman filter uses. And finally, I'll give you some so I take my secret value and a dispersion, and I run my sampler. I'm taking 10 values with a seed of 2. So that's that. Right, and now we can use Bayes' theorem. Right, so Bayes' theorem, if you remember, you just took. It's really hard doing this. I'd like to. Sorry for guys over there. You take the the guess. So you've got loads of these guesses, remember, in your histogram, and you say, well, how likely, oh, sorry, these are the guesses. You say, how likely, given that bit of data, is that guess? And you multiply it by the height of the guess in the histogram. So highly likely guesses will get a big weight, and if it was the original histogram, you'll multiply it by a big weight. Right? It's probably easier when hopefully I'll show it on a picture, yes. And then we just run this function. Shall I say a bit more about this? Yeah, and then we just run this function, this function that creates the posterior over the data, and create a sum of the data. I want to show you a picture. That's what you get after you've done one observation, and you run that so you take every guess, you run the posterior for every guess, and you get a new histogram. So I'm just going to go back and explain a bit more about what that's doing. So these histograms, which come from the histogram fill library, you can map every value in the histogram. So here I am summing all the values in the histograms, and then normalizing the histogram. So otherwise the histograms will be different heights. D is the data. Where are you? Oh yeah, that's if you remember, that was the data from the previous. There, yeah. So I've created a load of data that I give to you, and then you use it using Bayes' theorem to give you a new histogram each time. So here's your histogram after one observation, and then after 10 so you can see it's not really moved very much. So actually, I should have printed out the first item of data. I think it was about -1 or something crazy, the first one. So the histogram didn't move very much. But after 10 values, because don't forget, my secret value is 1. You'll get a load of values centered around 1. After 10, your guess has moved to being near 1, and you're much more certain now. If you see, the spread has got very much narrower. So that is how you use Bayes' theorem to estimate a value. Okay. So now you have a different problem. I'm not another game, I guess, but you're now, imagine you're Robert Brown looking down your microscope in 1827, and you're looking at some pollen on a slide, and you see this bit of pollen sort of moving around randomly on the slide. And this is what came to be known as Brownian motion, named after him. And but you're living in the 21st century, so you don't want to have to keep moving the slide around yourself to keep it in the center of the pollen grain in the center of the microscope. You want to use a motor to do that. So you want to be able to track that pollen as it moves around on your slide. So we can now you get some equations, but are hopefully not too complicated. So you can just we can just model the motion of the pollen particle as a pair of horizontal and vertical, and it's just, this is white noise. So we don't know how the particle is going to move. It's just going to move randomly in each direction according to some white noise. So I don't know what that would feel like to the pollen particle. Well, I suppose it would be jiggering around quite rapidly and violently. So if we rewrite this as a matrix equation, writing x, we rewrite. We want to get rid of the fact we've got second order differential equations here. We want to rewrite it as a set of first order differential equations. So what we do is we just create some new variables, x3 and x4, and then we can write down that pair of equations as this matrix equation. So if we take that, multiply it by that, x3, so we've got dx1 equals x3 plus nothing, which is what we said here. Is that right? Yes, dx1 by dt equals x3. So you can do all that. Everything works as you'd hope. But we don't want it in continuous time, so we're going to discretize this and move forward things delta t at a time. So let's say 0.1 of a second or something like that. So now you can see that x1 equals the previous x1 plus delta t times x3 plus now I've changed the white noise and I've got a random variable that is normally distributed, right? So that's what white noise is. If you integrate it over time, you get a normal variable, a normally distributed variable. So now I've got some Gaussian noise or normally distributed noise plus some equations that tell me how to step forward in time. But I'm not going to tell you the velocity at each instant. I'm only going to tell you the position. So I'm only going to allow you to observe the position, but worse than that, I'm not going to allow you to observe the exact position. I'm only going to allow you to observe a noisy position. So I'm going to add some more noise on here to the position that you're allowed to observe. Because presumably that's what happens, isn't it? Your camera's not going to be able to observe the velocity. It can only observe the position, and it really can't, there's going to be some error in the camera of where the particle is, or where the pollen particle is. And finally, I can write those down in matrix form. So x, the new x equals some linear function of the old x plus some noise. The observation is some function of the current position, position and velocity, current state, I should say, plus some more noise. And that is my model. That's what that's what I've told you is going on in the pollen particle under the microscope. So we can play the same game. I'm not going to go through a derivation now because it takes a lot longer to go through the derivation. First, I'm going to sample my secret value. Well, it's actually a path now. So, I mean, I'm pretending I'm some sort of super being where I can observe at all time. Well, time's is irrelevant to me. So I'm going to create a path of the noisy data, and I'm going to create a path simultaneously. I'm going to create the observations because I can do them both at the same time. So this is just me simulating what the pollen is going to do, or what the pollen does do. So here we are. So I'm taking the model we had above. I'm taking my old value of the state, multiply it by the matrix, using, this is the H matrix operator to do matrix, to multiply a matrix by a vector by a matrix. I'm adding some noise with the amount of noise described by Q. That gives me my new state of the system. I'm then only allowing you to see the position part of the state, and I'm adding in some more noise, again using the normal distribution. And I'm returning this as a pair, and that's the new state, so I can run it through, just use it as a way of stepping through to get my samples. So I don't want to go through how the unfold works, but that was just how I decided to create a path using the previous state. So I'll give you now. I did start off trying to do this in 4 dimensions, but realised doing histograms in 4 dimensions wouldn't translate very easily to the screen. So I've pretended. So now the pollen particle is only allowed to move in 1 dimension. So I've only got 2 dimensions in my state. I've got the position and I've got the velocity. So I'm using 2-dimensional histograms now. And so here's my starting value. So it starts at position 0 and it's got a velocity of 1. Here's my how spread out, how random the, this is what I'm choosing it from. So your initial guess will be described by how spread out the distribution is. So this is me describing, so I'm saying your initial guess ought to be this, but it may not be, and how far away, how uncertain you are is described by this matrix. So now I create a new histogram, but this time it's a two-dimensional histogram. So this is your initial guess as a histogram rather than as one value. And I can't, well actually I couldn't find a good way of doing this in Haskell of producing 3D charts. So I just produced so I've projected onto the x-axis, I've projected onto the y-axis, or the x1 and x2 axes, and now we can look at the what your guesses are for position, what your guesses are for the velocity. So your initial guess for the position, this is without any data, is it's something centered around 0, and your initial guess for the velocities, it's something centered around 1. So here's the model. We've already talked about the model, which is the state gets updated by this matrix multiplication, got some noises added in. Now we want to see how good your guesses are. So now we take the ooh, that's wrong. No, it's not, sorry. We take the current value of the state, we extract the observation, and we add the noise, and we see how close it is to our observation. All right? So that's the model, right? And you're given that. So now you can use Bayes' theorem again to track the path of the pollen. So we take the initial histogram, your original guess, you take your bit of data, and we are going to create the new state. Oh, I had to do all this because I couldn't do monadic values on histograms. So the guy who wrote I can't remember his name now. It's a really good library anyway, the histogram library. He's hopefully going to add a monadic update value to the library, but I had to turn it into a list. So that's me turning the histogram into a list. Then I can update the state from the list monadically. Then I can, I have to create a new histogram then from the updated state. And I have to make sure it's weighted with the correct values from the original histogram. And here's the actual Bayes step. So we do the weight. How far is our guess in the histogram away from the bit of data times the height of the histogram, and that gives us a new histogram. Oh, and we add in the noise. Oh, sorry, UQ is the histogram, not the noise. So here's our estimate for the position after one observation. So you can see now, we think the position, well actually it's hard to see on here, and I'll prove that it really has moved forward a tiny bit. So my time step was about 0.1 second, I think. So now we're really certain where the particle is. It's just after 0. It's 0.1 because we're moving at a velocity of 1, or we guessed we were moving at a velocity of 1. And so our guess has gone down from being quite a wide guess to quite a narrow guess. And here's our velocity estimate after one observation. So that's centered around about 1. And given the actual data, I think I show you the data. Here we are. Oh yeah, here we are. Given the actual data, here was the velocity was actually 0.7, so it wasn't moving as fast as we thought, but its position is almost exactly 0.1 away from the origin. So we've done this. So rather than rely on our eyesight and histograms, let's look at the marginal distributions again. So we sum down the x-axis, we sum down the y-axis. Using the histogram library, we can create the mean of the marginals again, and then print out the mean of the marginals. And looks like our position, we've guessed it as about 0.98. Sorry, that's a velocity, 0.98. So that's quite good. And the position is around about 0.1, which is what we'd expect, really. So that is how you do, well, it's not Kalman filtering, is it? No. But that's what's going on underneath the covers of Kalman filtering, is you're getting these guesses, you're getting data, you're getting better guesses as you get more and more data. Right, so what you say to yourself, wait a minute, in 1968, could they really have done all this parallel computation? Did they have enough memory? Did they have enough power to do this? And the answer is no, they didn't, right? So they didn't do it this way. How they did it was a load of algebra, right? So remember, our model was quite specific, right? Our model could have been, there was nothing in what I just did which says your update has to be linear and your errors have to be normal. There's nothing in that was just a choice I made, right? So that's our model. We've got a linear update, we've got linear observations, and we've got Gaussian or normal noise for both, right? So that allowed people like Kalman to do a lot of algebraic manipulation and come up with this, which is what I didn't want to show you. Yeah, trying to explain this, you'll lose the wood for the trees, right? So this is what they actually implemented and what I've actually implemented. So there's a whole load of matrix manipulation, transposes, inverses, but don't forget these aren't very big, right? So we're only talking about three-dimensional space objects with a three-dimensional velocity. So you're only talking about six-dimensional matrices. So computers in the 1960s were very capable of doing that sort of calculation. Right, so here is my implementation in Haskell. Almost the same, right? So quite nice. So I couldn't find a very good way of doing transposes as a postfix operator, so I gave up. And so for the inverse, yeah. So I've had to stick with those, I'm afraid. But these are the operators from the H-matrix library. So if you want to do matrix multiplication, this is your, well, my first port of call anyway. Right, but the problem is, and where I went wrong, right, is I mixed up those two matrices, right? And if you happen to be testing with, and you made your observation space the same dimension as your state space, which I did, and I'm obviously an idiot to do that, then it's easy to swap these around, and even at runtime you won't get an error because the dimensions all match, right? So after, potentially after a lot of debugging, you realise you swap around those matrices, and you could do it almost anyway. Why not swap rows around if they were the right? At runtime, they have the same number of matrices. Okay. So one thing you could do is you could annotate your code with what you think's going on. Right? So you could say, well, I know the dimension of the state matrix. Yeah, that one should be a what should it be? A square matrix of n. So it should be an n by n matrix, and the observation matrix should be n by n because we're going down to a smaller dimension. So you could do all that annotation, but you could still get it wrong, couldn't you? I mean, it might help. So even better, wouldn't it even better if instead of having to do all this by yourself, the compiler told you? Yeah. So if you use the right bit of H matrix, it does tell you. So I didn't need to do this, right? I didn't need to put in the type annotations. They get inferred for me. But I could go in and put the type annotation in there, and then I could actually sort of think, oh yeah, that is the right, that has got the same dimension as that. So subtracting them makes sense. I mean, the type checker is telling me that. So that's what I really wanted to get to. That's the whole point of the talk, is by using type level literals, so making sure the dimensions of the matrices are in the types, I avoid some, but not all problems. I've got some better chance of making my Kalman filter correct. Obviously, I've got to test it, but now at least I know I'm multiplying them using the right matrices in the right places. And that's it, really. So I just wanted to recommend, if you're doing any matrix stuff, use the H matrix static part. Oh, I should have said, actually Tom's not here, but he always says to me, but how can I use it, supposing I'm reading in my matrices, how can I use a statically typed function? Oh, he is there. Oh, sorry, he's hiding behind Graham there. Okay. So there is a function in the library now which allows you to do, so you just say with, right, and then you can lie about the size of your matrices and hand them over. But the actual algorithm's correct. If you lie about the size of your matrices you're handing into it, I think that's, it's down to you. And you probably will get you won't necessarily get a runtime error depending on your model, but I think it's down to you to make sure your matrices are correct when you pass them in, so you can lie about their types. I think that's all I wanted to say. Yeah, so the computer really helped me get my Kalman implementation correct.
Is there a with alias for unsafe coerce?
Has it got unsafe? No, it's not. It's not unsafe coerce. No. It's using existential types, so you don't have to do anything bad. But you're still lying, right? And so you can still fail, either with a runtime error, or it might not fail at all if your dimensions all match. Yeah. Right. So you can do even better actually. So H matrix only deals with matrices and vectors, but there's lots of applications where you want higher rank arrays. I won't call them tensors because they're not really. And with Neperian functors, or they're really representable functors, you can do even better. So we can do, hopefully if I ever get invited back, I'm beginning to have my doubts, then you can do things like variation inference in Haskell. And it looks like APL, but with the advantage that it's all type checked. You can't get the ranks. You won't end up messing up that part of your array, that sort of rank of your array with another rank of your array, because the types are going to be different. And you can see, Jeremy, if you're interested, Jeremy Gibbons got a great paper on that, applicative programming with Neperian functors. I just want to do a shout out for H matrix, we talked about that. Histogram, if you're doing histograms, histogram fills a great underused library. It really is. Anyone doing data stuff, Tom, should be using it. And random foo for random variables. So yeah. Oh, and I should say, there's my very own Kalman filtering library. I didn't write it on my own, I should say. Jacob West was one of the principal authors, which does not just Kalman filtering. It'll do unscented Kalman filtering. It will do extending Kalman filtering. So if your model is not linear, it will linearize it and apply the Kalman filter to the linearized model, and particle filtering as well. So where you can be much more general, but you need a lot more computing power. I mean, I really told you about particle filtering, not about Kalman filtering. And smoothing. So smoothing is where, filtering is where you want to know where you are now, given all the data you've had up to now. Smoothing allows you to take values, well, if the clocks run forward, you've actually got more information now about where you were. So if you were let's say the Russian jet that overflew Turkish airspace, or possibly overflew Turkish airspace, you could use Kalman smoothing to see whether you really overflew Turkish airspace. There we are. Oh, yes, I was going to do somewhere, not there, here. So here is, I've broken with tradition here. Traditionally, no Haskell package has any documentation, and you're supposed to know everything from the types. So I've gone a bit overboard here, and I've written in quite a lot of documentation. So you hopefully be able to say, I can see from the Wikipedia article or the tutorial on Kalman filters, I just read what the model looks like. There you are. Mathematically, there's a little example of a pendulum, a noisy pendulum. You're only allowed to observe the horizontal displacement of the pendulum. Oh, and it's highly non-linear because I'm doing the real equations of motion for the pendulum, not the linearized ones we all do at school. And there's the code that does it, and there's a picture of the. You've got actually I didn't. That's bad of me. There's actually two vertical axes. One for the where the pendulum is, and the other for the observation. So if you think, wait a minute, the observations are all above the estimate. Why are you estimating? That's because that's the horizontal displacement, which is on a completely different axis, which should have been here. And there you are. It's doing quite a good job, really, the extended Kalman filter for finding it. I think the unscented one does a bit better, actually, in my view. Anyway, there you are. You can download it and try it out. Thank you.
Okay, I think we've got some questions.
Okay, I've actually two questions. One, the more practical one. When you're working in linear algebra in Haskell, how do you actually spell your variables? Because you probably have lowercase.
How do I spell them?
Yeah. I mean, can you use capitals somehow?
No.
Yeah.
If it's an uppercase variable, I prefix them by big. So I say big Q or
Okay.
big K.
Well, second.
I mean, yes, I've got the typesetter to change them to Greek
So
letters. Yeah.
Cool.
Yeah.
It does, even with holes.
Yeah.
Okay. Cool. Then.
Yeah.
Yeah.
Sadly, yes. There's no really good answer, I think.
And then second, you with H matrix, as far as I understood, you got things correct up to matrix sizes. But
Yeah.
are you aware of a technique in Haskell where you would annotate on a type level the like what the rows and columns mean of a matrix? Say?
You can. There is a
Probably
Unix
can
package.
be done, but
It can be done. I haven't. Yes, I have done it. Yes, I've got a blog post that uses units quite extensively, and I think also uses H matrix. But I didn't use the static part of H matrix, for which I apologize. I should have done, but I didn't. I don't know why. Yes, you should. I haven't tried it myself, but I'd see no reason why the units stuff and the dimensional stuff shouldn't work together quite nicely.
Any more questions? Okay, well, let's thank the speaker again.